14.5 is the area problem, or the integral. So in this class, we are going to estimate area under a curve using rectangles. So if you have this function here, f of x, we're going to estimate the area between a and b by splitting it up into a certain number of subintervals and creating rectangles out of it. So the area of a rectangle is base times height. We're going to split this into an even number of rectangles, 4 or 8. This one, for instance, so I have 4. And all of their bases are going to be the same. So that I'm going to call delta x, and then their heights are going to be the y coordinates at each of those points. So the area of this rectangle, for instance, is delta x, or whatever the width is, times the y coordinate here, f of u. And then you're going to sum that up, or add all 4 of them up, or add all 8 of them up. We have two ways that we do that in this class. We do left-hand sums, which is what I have drawn here. For every rectangle, you pick the left-hand point to be the y coordinate. The other way that we do it is right-hand sums. So for right-hand sums, what I have drawn here in purple is for every rectangle you pick the right-hand point, and that's going to be the height of your rectangle. So that's how we estimate area under a curve in this class. So let's try one. We have the graph y equals x, and we want to find the area between the curve and the positive x-axis from 0 to 5. So first thing, we're going to split up, I'm going to draw my endpoints. So you have x equals 0 and x equals 5. So it tells us we want to split 0 to 5 into two equal subintervals, and for our rectangles we want to make the height the left-hand endpoint. So if we want to pick two equal subintervals, we can find our delta x, or our width of our rectangles, as the difference between the endpoints divided by how many subintervals you want. So in this case it's 5 minus 0, our endpoints, and we want two subintervals. So each subinterval is going to be a width of 2.5. I'm going to split this interval from 0 to 5 in half and put a line at 2.5. Then it wants us to choose our endpoint, or our height, as the left-hand endpoint. So if we're looking between 0 and 2.5, our first rectangle, which is the left-hand endpoint? So 0 is the left-hand endpoint. So I'm going to go to the height of 0, which in this case is 0, and that's going to be the height of my first rectangle. My second interval, between 2.5 and 5, I want to pick the left-hand endpoint. The left-hand endpoint is 2.5, so I'm going to go up to its height and make that the height of my second rectangle. So I have one rectangle here and one rectangle here, and that's how I'm going to estimate the area underneath this curve. So is this going to be an over approximation or an under approximation? We have all of this extra space up here, so this is going to be a under approximation, but we're still going to use it. So area of a rectangle is base times height. In this case we have two of them, so we're going to add them up. So if we look at our first rectangle over here, our base is 2.5, our width is 2.5, and our height is whatever f of 0 is. So we're going to multiply that by f of 0, the y coordinate at 0. For our second rectangle, our width is also 2.5, and our height is the y coordinate at 2.5, so f of 2.5. What you'll notice with these is the width, or the base, are going to always be the same, because it's going to be whatever this delta x is. So a lot of times I just factor that out. I know that's going to be the base for every single rectangle, so then I'm just going to add up the heights, f of 0 plus f of 2.5. Well, f of 0, the height at x equals 0 is 0. The height at x equals 2.5 is 2.5. So then I'm just going to plug this in my calculator and figure out my area of these two rectangles. So if you plug this in your calculator, you end up with an area of 6.25. So our estimation of the area under the curve is 6.25. For this one, we can actually find the actual area. It makes a triangle. So go ahead and pause the video for a second and find the actual area under the curve. So it's a triangle, so you get 1/2 base times height. The full base is 5, the whole height is 5. So the actual area is 12.5. We know this because it just makes a triangle, but most curves aren't going to make a nice easy shape. So you can see how much of an under approximation this was. So now we're going to try the same thing, the same problem, but instead of a left-hand endpoint, we're going to choose the right-hand endpoint. So when you look at your first subinterval between 0 and 2.5, we're going to pick the right-hand x-coordinate as our height. So between 0 and 2.5, 2.5 is our right hand, so we're going to make that the height of our rectangle. And then between 2.5 and 5, our right-hand endpoint is 5, so we're going to make that the height of the second rectangle. So we're going to estimate the area under the curve using these two rectangles. We're going to use the same exact method that we did on the previous one. So go ahead and pause the video and estimate the area under the curve. So for this one, again, all of our bases are a width of 2.5, so I just factor that out and then add up our heights. So for our first rectangle, we use 2.5 as our height, so we want f of 2.5, the y-coordinate there, to be our height for the first rectangle. For our second rectangle, we use 5 as our endpoint, so the height is going to be the y-coordinate at 5. So I have 2.5 times 2.5 plus 5, those are the y-coordinates, or the heights. Multiply that all together, and you end up with 18.5. So this was an over-approximation because both of our rectangles were above our line. And that's fine, that's just your answer. This is just an estimation. So now we're going to do the same thing again with the same graph and the same interval, but instead we're going to split our interval into 5 equal subintervals. So when we find delta x, it's still going to be 5 minus 0, b minus a, but now our n is 5 because we're splitting it into 5 subintervals. So each subinterval is going to have a width of 1 instead of a width of 2.5. So when I split this up, that means every 1 unit I'm going to have an interval. So I'm going to have 5 rectangles instead of 2 rectangles. So what is this going to do to our approximation? Is it going to make it better or is it going to make it worse? The more you have, the more accurate you're going to be. So it's going to make our approximation better. We still want a left-hand endpoint. So between every interval, we're going to pick the left-hand interval. So when we look between 0 and 1, our height is going to be at x equals 0 because that's the left hand. Between 1 and 2, we're going to pick left hand, which is 1, and that's going to be our height. Between 2 and 3, we're going to go choose 2 because that's on the left. 3 and 4, we're going to choose 3. 4 and 5, we're going to choose 4. So our approximation now are all these blue rectangles. So are we going to be an over approximation or an under approximation? We're still going to be an under approximation because we have all this extra space, but it's going to be a better under approximation than the first one. So go ahead and pause the video and find the approximate area under this curve. So our width, or our base for every single rectangle is 1. That's whatever your delta x is. And then our height are each of the y-coordinates at whichever endpoint we picked. The number of heights you have should always equal the number of subintervals you have, because that's how many rectangles you have. So we have 5 subintervals, or 5 rectangles, so I should have 5 heights. In this case, it's the smaller number, so f of 0, f of 1, f of 2, f of 3, and f of 4. So come all together, multiply, add, and you end up with 10. So it's still less than that 12.5 that we know the exact value is, but it's better than that 6.25 from the first example. So now try the same thing, but with a right-hand endpoint. So 5 subintervals, but with a right-hand endpoint. So we split 0 to 5 into 5 equal subintervals, so every unit is a subinterval. And then we wanted right-hand endpoints. So in every subinterval, you're going to pick the right x-coordinate, have its y be your height of your rectangle. So it's still going to be an over approximation, but when you do this, you drop off, so you're going to still have 5 heights, but you're going to drop off the f of 0 and add the f of 5 on the end. All these middle ones stay the same. So you end up with 15. So it's still bigger than that 12.5, but better than that 18.75 of the first example. So now we're going to try y equals x squared. So this one, we can't just use a triangle to figure out the actual area. So this is just going to be an estimate again. So using 4 equal subintervals, so that's our n, we want to split up x equals 1 to x equals 5. So first thing, go ahead and pause the video and find your delta x, your width of each subinterval. So you're going to split 5 minus 1, so this width of 4 units, into 4 equal subintervals. So each interval is going to have a base of 1. And now we want left-hand endpoints. So do the same thing we did for the previous examples, left-hand endpoints, to estimate the area under this curve. So for each subinterval, we're going to pick the left-hand endpoint. So between 1 and 2, we're going to pick 1. That y-coordinate is going to be the height. Between 2 and 3, you're going to pick 2's y-coordinate. Between 3 and 4, you're going to pick 3. Between 4 and 5, you're going to pick 4. So is this going to be an under approximation or an over approximation? All this extra space in here means you're going to have an under approximation. Your width of each rectangle is 1. The height is the y-coordinates at each of those left-hand endpoints. So f of 1, f of 2, f of 3, and f of 4. So you end up with an estimation of 30. The only way at this point that we can do this, find the exact value, is with your calculator, your graphing calculator. We'll do that in class. But just so you have kind of an idea, the actual area under the curve is 41.333 on forever. So now try the same thing, but with your right-hand endpoints. 4 subintervals, right-hand endpoints. So same thing, each delta x is 1. You're going to pick the left-hand endpoint, so you have your heights as f of 2, f of 3, f of 4, and f of 5, and it totals up to be an area of 54. So this is, again, an over approximation, but this is just your answer. So the way that we measure area under a curve is called the integral. So the area under a curve, A, is equal to this thing. That's basically saying do what we just did, but make your number of subintervals go to infinity. Don't worry too much about the definition of an integral. What we care about is this integral notation. So you have your integral notation. We're doing it from A to B, so those are your endpoints. Left hand on the bottom, right hand on the top. Whatever the function is, and then dx. So for instance, for that last example, you have the integral from 1 to 5 of x squared dx, and that's the notation for integration. So to estimate area under a curve using rectangles, we have your interval, divide that by how many subintervals you want, and that's your delta x, or the width of each rectangle. And then you have to read whether you want left-hand endpoints or right-hand endpoints, and then pick those y-coordinates to be your heights. And that's just your answer. That estimation, over approximation or under approximation, is just your final answer for these.